Okay, so in the previous lecture, I was talking about various aspects of second order optical nonlinearity and molecules. So, you remember we talked about supramolecular synthons, macrocycles, okay, macrocycles, then calixarenes, okay, and then your cucurbituryl, and then cryptands, so on and so forth. There were many. I spent several lectures on those. So, each of those compounds have been derivatized with donors and acceptors. Basic thing is we have to make donor pi acceptor somehow. Okay, that could be 3-dimensional, it is better, it could be better. We can use, I have not discussed phthalocyanine. Phthalocyanine is AJA macrocycle. Another important macrocyclic compound is porphyrins. So, all these things can be derivatized to have d pi a systems, and they will all give second order optical nonlinearity. Okay. So, my request to you will be you study these things in details. Okay. Their use of, I will now discuss one very important use of second order optical nonlinearity, that is SHGF, SHG. That is why I have written here, so that I do not forget today. SHG stands for second harmonic generation. Second harmonic generation. That means, I take one second order optically active compound, here it is. Okay. Suppose this is second order optically active compound. Now, if I hit it with H nu or maybe H nu 1, okay, not that, not photon, but suppose I put a electromagnetic radiation whose frequency is nu 1, then I can produce here, I can produce frequency 2 nu 1, that is called second harmonic generation. So, if I take a frequency nu, I could generate, nu is there, but I could generate also, in addition I could generate 2 nu 1, 3 nu 1 will be very little. So, ignore that. So, 2 nu 1, that means frequency doubling, that is called second harmonic generation. So, if I interact the, so this is where actually it is playing with light, okay, it is playing with light. So, if I use light and put a material which is shows second order optical nonlinearity. So, I put a light there, I get two different lights, one is the original little bit, and then I can generate second harmonic generation, then I can get a 2 nu 1. If I put a light of 500 nanometer, that is visible range, okay. 500 nanometer absorption is a blue color and it is a visible range. So, then I can get 500 nanometer wavelength, okay. So, I can get after passing through a second order optically active, second order nonlinear optically active material, I can generate 250 nanometer. That means, I heat it with a visible light, I can get UV light. Okay, this way, so these things are very second harmonic generation, they are very useful in laser spectroscopy. Okay. They are also used in defense. In defense, a plane is going, a plane is falling, plane is going, and enemy radar, to detect it, it will send one wave, okay, radio waves. So, if send one radio waves, this radio wave frequency will be, and if it has a second order, if it has second order optically nonlinear optically active compound material, say the plane has a coat of compound which is second order nonlinear optically active, then what will happen? This frequency will come here and it will interact with this frequency and change a different frequency. So, it will remain undetected by the radar. So, this photonics or optical nonlinearity is very important in defense. In defense, it is very useful. All right. So, the plane that you say, the stealth bombers and all that, they say they heavily used photonics. Okay. They change the frequency. So, basically we are playing with light, okay, changing its frequency from one to the other and all that by using nonlinear optically active materials. So, in second order, so one of the most important outcome of second order nonlinear optically active material is second harmonic generation, and it is very useful in optical data storage, telecommunication. Okay, these things are very useful. You do not ask me what is how telecommunication can be connected to this, I do not know. These are very specialized. So, some special people who work like on this, they will be knowing. Okay. All I know is how to make molecules with high beta values as well as high chi 2 values. That is what, as a supramolecular chemist, I know that. And what is my how I generate my ideas from those 3 points that I gave you. Okay. So, this was up to second order NLO. Now, I give third order NLO is again very important. Third order NLO is very important. It is called optical switching. Then it can see some in biology. We have if there is a third order NLO activity can be used to map a cell very accurately. So, those things are there. We will not be knowing the details of that, they are very difficult, not easy. But what we know, what we will discuss, that what is third order NLO activity. One thing is, third order NLO activity does not require the compound to be crystallizing in non-centrosymmetric space group, which was required in second order optical activity, those nonlinear second order NLO. Let me write NLO. So, second order NLO active compounds must be crystallizing in non-centrosymmetric, but third order NLO active compounds, there is no need whether it crystallizes in centrosymmetric or non-centrosymmetric, does not matter. It will always show third order optical NLO, third order NLO activity. Okay. So, third order NLO activity, how we measure third order NLO activity is measured by another term I am using, TPA. Measured by TPA means 2 photon 2 photon absorption. Two photon absorption. 2 photon absorption coefficient, okay. Absorption, we will say 2 photon absorption cross section. And it is expressed as sigma 2. Okay. So, third order optical nonlinearity, I would say that second order optical nonlinearity will depend upon, SHG can measure. If greater SHG means it is pretty good, second order NLO. If the TPA is very large, then it is a very good third order NLO, like that. Okay. And the expression that I will write right now, sigma 2 I will just write the expression without explanation. Why, you will understand. H cross omega square n square c square L4 imaginary part of gamma. Gamma is the third order NLO. Gamma minus is a function of minus omega minus omega is an equation. Okay. Now, L corresponds to local field factor, and then these values is expressed in GM. Unit is GM. 1 GM means expressed in GM, where 1 GM equals 10 to the power minus 50 4 second per photons molecule per molecule. Okay, so this is a something you should forget immediately, all right. We do not worry about this thing, but as a chemist we have something as a chemist. Okay. I will also say this 2 photon absorption cross section, little bit time, that will be understandable to you. Usually we have always go from ground state to excited state. It absorbs, the molecule absorbs 1 photon, single photon, and goes up. Okay, single photons. So, single photon is always very common. How about 2 photon? 2 photon I am writing. Okay. These are vibrational. Okay. Now, we have a virtual state. This is a virtual state. This dashed line, and this is my excited state. Okay. This is vibrational structure. So, the molecule 2 photon absorption, what will happen? It will absorb first H cross omega, this is your frequency, and then another this is the property of the compound that it absorbs single photon and go to the virtual state, and then another single photon go to the excited state, and this is ground state. Okay, so this is called, and then it okay, and then it can show fluorescence also. We called 2 photon fluorescence, that is 2 photon absorption and 2 photon fluorescence. 2 photon fluorescence is very important in biology, very, very important. All right, we will talk about it later if you have time. So, this is called 2 photon. So, which molecules will undergo 2 photon? The molecule with symmetry, okay, molecular guidelines gives you. So, in this second order NLO we had D pi A, that is asymmetric charge distribution. Donor will become positive, acceptor will take electron, means become negative. Okay. So, this is a plus delta, it will become minus delta. So, one side is plus, another side is minus, means it is not symmetric. Okay. Second order NLO, second order NLO, that is beta value, etc., etc. Third order is symmetric charge distribution, third order, that is what I am saying that. And third order means those molecules will have 2 photon absorption cross section. 2 photon absorption cross section means probability of 2 photon absorption process. Okay. By cross section we mean higher the cross section, higher is the probability of the molecule to absorb single photon, go to virtual state, another single photon, go to virtual state. So, 2 photon absorption cross section means the probability of the molecule to undergo excited to the first excited state by absorbing 2 photons. Okay, and that is expressed in sigma 2. Okay, so what, as a chemist I am not interested in this theory so that much, but what I am interested in, which molecules will give such 2 photon absorption, that is D pi D. What do you see? Both sides D, both sides donor. So, it is a basically is a symmetric charge distribution. Here is asymmetric charge distribution, asymmetric, I mean asymmetric charge distribution for second order, and for third order symmetric charge distribution, or it can have A pi D pi A, or it can have D pi A pi D. These are all conjugated structural motifs, and so the TPA phenomenon are expected to be obtained with this kind of charge distribution, symmetric charge distribution, that is very important. Some examples. Now, I give you some example. One of our example I will give you first. One of our examples would be, our compound was simple. So, what is this? This is a donor. This is a donor because nitrogen and this is CH3, CH3. So, due to inductive effect, nitrogen is donor and then this is a pi. Then after pi, single bond, then double bond, then single bond, then double bond, then nitrogen, aromatic, okay. Then double bond, same thing here also, then single bond, then double bond, then single bond, okay. So, my drawing is really ugly. I can do it little bit better if you want, probably you do, then I will make it little bit better, then I will remove that. Ugly thing is not to be tolerated. Okay. Now, it is looking all right. So, this is my compound. Okay. What is this structure if you look at it carefully? D, this is D, this side is D, this side is D, both sides D, and this side is A. Okay, it is a double bond, so it is A. I would say A, okay, and then pi, these pi things, okay, all these pi. Okay. So, this is my structure. Now, this A is not very strong A, okay, but weak A. A has also a strong, weak, everything. But if I react to it, what did I do? If I reacted with zinc, okay, zinc is 2 plus. So, it will attract electron towards it. That means, nitrogen will donate electron to this and nitrogen will donate electron to this. In the beginning, nitrogen was weakly acceptor. Now, because of zinc, it donated to zinc, it became very strongly attractive. That is what I mean. You understand that? Because nitrogen is now attached to, nitrogen likes tetrahedral. So, there will be another of this tetrahedral. Okay. So, what I am saying is, I would say this was D pi, then A star, pi D. Before metal, it was like this, pi star means weak pi, means pi is not very strong, strongly, not weak pi. I am saying pi, writing A to do it carefully. this A and this A are very weak A, but if I put a zinc 2 ion, what happens? Weak A, that means it wants something, it wants electron density, but because of zinc 2 wants more electron density. So, it will accept electron density from here and here, because these are donor, nitrogen donor. Then it will become strong. It was weakly accepting, now it will be strongly accepting. Because it will be strongly accepting, let me remove the star mark. So, now if it is doing like that, one more here. So, this will give a, so now what is the values? Let me write the value. Okay. So, the value, what value? That unit, sigma 2 values. Okay. What was the unit? I told you GM. Okay, GM. So, sigma 2 is 10,736 GM of the zinc complex, and without anything, just the ligand means nothing, just the ligand means d pi A star means weakly accepting, their sigma 2 value was 170. So, you can see because of this it enormously increased GM, and 10,000 GM is very good, 10,000 GM is very good. So, this was our work and we did it with zinc. Now, there is a question will be asked, why we did use zinc? There are so many metals. Zinc, because zinc is white, it does not have any signature, spectroscopic signature. We can use zinc 2 plus, we can use copper 1 plus, because they do not have no spectroscopic signature. So, here I am showing you this kind of structures, and a metal ion can increase, a metal ion can improve its third order NLO activity. Okay. So, from here on we will again try something else from next day. Thank you very much.